All right, we'll get started. We should get started. So far we have been discussing the growth function. And what we have shown is that the growth function for an hypothesis class is bounded by n to the dvc of h plus 1. So it actually increases polynomially in the number of data points. Now the reason why this is useful is that we can develop bounds on the generalization error in terms of the growth function. So what we can show is the following. The second theorem, it says that the probability that E in of G minus E out of G, so if G is any element in H selected in an adaptive way, so after looking at the data set, the probability that this is greater than epsilon, which if you recall is less than the probability of the union of H in H, E in of H minus E out of H greater than epsilon. This quantity is now less than K1 mH of 2n times e to the minus K2 n epsilon square, where K1 equals 4 and K2 equals 1 over 8. So K1 and K2 are fixed constants. K1 equals 4 and K2 is 1 over 8. So you have very similar bound like we had when we did the union bound up analysis. There we had mH of n was replaced by m, the size of H, the total number of hypotheses. So the m in the previous bound now essentially gets replaced by mH. There are certain tweaks here. So you have mH of 2n instead of mH of n. So there's a slight change here, and the constants are somewhat different. You have 1 over 8 instead of 2 in the exponent, and you have a 4 here. So it's not exactly the same. Previously we had a bound like 2m e to the minus 2n epsilon square. So K1 was 2, K2 was 2, and m was the number of hypotheses. So we got a big improvement from m to mh, because m could be infinite. mh is typically a small quantity. It's upper bounded by this expression. We got a huge gain here, but we did pay a price slightly in terms of what the constants are. They are slightly weaker now. Right? That usually is not a big deal. This is a huge improvement.
But then, like the stuff that we did in the past, like in the past half, right? For the MH, we looked at the vectors with the same E in, right? But then we don't take into account the E out.
That's a great question. So the intuition why we could improve this is that if you have two hypotheses that have the same dichotomy vectors, they will have the same E in. So instead of taking union, imagine this was a constant, this was always 5, right? Then if you take the union over all hypotheses, it's equivalent to just taking the union over different dichotomy vectors, if E out was fixed. Because then the only event that matters is the value of E in, and if two vectors have the same E in, if two hypotheses have the same value of E in, then they will give the same event. So if E out was fixed, then it is clear that this union just requires union over all MH, and you would have MH of n. There is a slight change here. You have MH of 2n. And this 2n comes from the fact that E out is different for different hypotheses. So the way, if you look at the proof, the way they do it is that they write E out as an average over a fresh set of n samples, different from training. So they write E out again as the average error, classification error, over a new set of n samples. So you have n samples from the training set and a fresh set of n samples, and they approximate E out as the average over a fresh set of n samples. And then that's how they get a total of 2 for good reasons. So the proof is in the appendix, and it is optional, meaning that you are not responsible for it. You can look through it. All you should understand is why we can replace m by mh, and why the growth function and dichotomies are important. We just want you to understand the intuition, not the tedious details in this proof. This proof will require a significant effort. It is like the level of a research paper. So any questions? What the result is? So the main point is, because this is increasing as a power of n, and this is increasing exponentially in n, for sufficiently large n, this term can be made as small as possible. So which means that if n is very large, this right-hand side will vanish to 0, and the probability that the in-sample and out-of-sample error for any g adaptively chosen, the fact that they are different by any threshold epsilon, will be arbitrarily small. So the two will be same with high probability if the value of n is large enough, right? So this means that learning is possible. If this quantity was increasing with n, if this was 2 to the n, then this product will not go to 0, which means the probability that they are distinct can be high, and then learning is not possible. So for any hypothesis class where the VC dimension is finite, learning is eventually possible if you have sufficiently large data set. That's the value of this bound. We can also express it in terms of confidence levels. So you can set this to delta, and then you can solve epsilon in terms of delta, right? So with confidence level of 1 minus delta, what we can show is that E out of G is less than E in of G plus a penalty term. And that penalty term is obtained by substituting epsilon in terms of delta. So you go back in that equation we just had, and you solve for epsilon. And epsilon turns out to be 8 over n log 4 mh of 2n divided by delta. We work it out. So all you have to do is go back here, and you set this to delta, so you have to solve for epsilon in terms of delta. So k is 4, and this is 1 over 8. So if you work it out, you will end up with this. You can check it. Okay. This is known as the penalty term, right? Because this is how much more the out of sample error can be. If your training error is small, the test error is going to be the training error plus a penalty term, just like we had before. Now mh of n is n to the dvc, right? This is polynomially increasing in n. Okay, plus 1. So if you substitute here, then you get dvc n, like log of n to the dvc. So it's not hard to see that the penalty term is of the order of theta of square root of dvc of h by n log n by delta. So again, I'm using the complexity notion. This theta means that it's between O and omega. It is the exact scaling, right? And it says that the penalty term scales as square root of the VC dimension as log n by n. So if you increase the samples, then the penalty term will decrease as square root of log n by n. If you fix n and increase the VC dimension, the penalty term will increase as square root of dVC. So if a model has a higher VC dimension, which means that it is able to shatter more points, then its complexity will be higher. And its penalty, the penalty term you have in this expression will also be higher. So it is more likely to overfit. If a model is simple, it cannot shatter too many points. Then the VC dimension will be small and the penalty term is going to be small, which means that E out will be close to E in. So the way to understand this expression is to just do the same sort of plots we had before. So we can sketch the error now as a function of the VC dimension. So if you have a linear model, it will have a small VC dimension. We'll see what the VC dimension is later on, but our linear model is simple, so it cannot shatter too many points. In 2 dimensions, it can only shatter 3 points. We saw that before. If you have a quadratic decision boundary, so if your decision boundary is some sort of a quadratic function, it is more complex than a linear model. So it will have some higher VC dimension. If you have a neural network, it might be here. It will be more complex, so it will have a higher VC dimension. So we'll study the VC dimension for linear models later on. All I want you to see is right now that we can order the complexity of different hypothesis classes based on their VC dimension. For each one, we can compute what the VC dimension is based on how many points they are able to shatter, and then we can order them along the x-axis. Now, typically, the training error will decrease like this. If you look at the training error, then the more complex the class you have, the smaller it will be because you will have more parameters to fit into your training set, right? The penalty term might be like this. It increases as the square root of the VC dimension. This is for a fixed n. As you increase the VC dimension, your penalty term is going to increase as square root of the VC dimension. Now for the test error, you have to sum the two. So E out will look like this. It's going to be the sum of these two curves. So initially it will decrease because the training error is decreasing. At some point, you will have the optimal VC dimension where your test error is the smallest. And then it will start increasing because the penalty term now becomes important. So this is the ideal VC dimension that you should have for your model. At this point, you are at a sweet spot because your training error is not very big and the penalty has not yet kicked in. So this is where your model is not too complex for overfitting and reasonably complex for the training error to be small so you can extract features from your data. Okay? So can anyone tell me where is overfitting and where is underfitting in this curve? Where is overfitting? Right? Here, this is the case when E out is large and E in is small. So as you increase the VC dimension, you're using more complex models and you end up overfitting. If you decrease the VC dimension, your in-sample error is large. So here, you are underfitting. And again, you can see the trade-off between model complexity and generalization error through this analysis.
I was wondering, so knowing the G, right? Can we kind of like have an idea what kind of hypothesis class would be most useful?
You could, for example, if you go from linear to quadratic to polynomial, like third order, fourth order, Your training error will keep decreasing because you're getting, so you can get an idea of what more order of nonlinear transform to use, for example. We'll go and discuss this more. So the question was, like, if we have, there are two parts to it. Given a number of training, given a certain size of training set, what is the right VC dimension to use? So this model gives you this kind of analysis gives you one idea, but there is a general rule of thumb that we'll discuss next. And the second is, if you now have a VC dimension, which model should you construct? For different VC dimensions, this quantity, the penalty term is the same, right? So then you should construct a model that gives you the smallest training error for that particular choice of VC dimension. So that is now our art of finding which model best fits the data. You are now free to select a model with a constant VC dimension that minimizes your training error. So there is a rule of thumb that is important in practice. So if you are given n training points, the VC dimension that you should use to make sure that you are not overfitting, that your generalization error is reasonably small, is given by n over 10. Or the number of training points you need to have a certain VC dimension is 10 times that many points. So n is the number of training samples. Say you have 100 training samples, then you should use a model whose VC dimension is no more than 10. That will guarantee that you are not overfitting, the penalty term is small, and if you have a small training error, the test error will be small. Okay, so this is a useful rule of thumb in practice. If you have a very big data set, millions of points, you can use a complex model with high VC dimension. If you have very few, if you only have 100 points, don't have a very complex model. The maximum VC dimension you can have is at most 10.
How does that come?
This just comes as a practical rule of thumb. It is motivated by this analysis. Like if you put D to be like 1/10, then this term is typically going to be small for most reasonable values of n. So this is the textbook gives this rule of thumb. So as a practitioner, you don't have to always go back and do that analysis, right? You just want to convince, like, given a certain amount of training sample set, what is the level of complexity to use? And this is the practitioner's rule of thumb, that this is the property. If you satisfy, then you won't have overfitting in most cases. Okay, so I have been talking a lot about VC dimension. The question is, how do you compute it, right? What is it for some popular models? So we'll do one in the lecture. We'll do the VC dimension for linear classifiers. So now we will assume that we are in D dimensions. So our data points are x1, x2 up to xn, which are all in D plus 1 dimension space. This is D plus 1 because the first term is the bias term, as always. This is just the same terminology we had when we studied the perceptron algorithm, logistic regression, and so on. We always augment a bias term to all our data vectors. That's why we have D plus 1. Okay? Our decision rule or our classification rule is that Y is sine, SIG and sine of W transpose X, where W is W0, W1, W2 up to WD. So this is a D plus 1 dimensional vector. So we have the weights, and this is basically drawing a line in D plus 1 dimensions or hyperplane. and one side of the plane the decision is positive, the other side it's negative. So this is the hypothesis class that we are interested in, linear classification. And the claim is that the VC dimension of this is d plus 1. So in d dimensions, the VC dimension of linear classification is d plus 1. That is what we will show. So in other words, if you have say a 10 dimensional data vectors, your VC dimension will be 11. And then the number of points you need to make sure overfitting does not happen will be like 11 times 10, like 110. That's the value of this result. If you know the VC dimension, you can decide what size of training set to select to make sure overfitting does not happen and your generalization error is good. Okay? Okay, so I have a question. If I gave you this result, can someone see why this is reasonable based on what we have discussed so far? Or would you be skeptical, like you think this is not the right result? It might be something else. Can someone give an intuition why this may be the right result? Why do you expect the VC dimension to be d plus 1? Okay, so the one good point is that, well, we know we have done one example before when d is 2. When d is 2, we were able to shatter 3 points and 4 was a break point. So the VC dimension was 3. It's consistent. So that's a good place to start. Always check what you know. That's good. So it is consistent. When d equals 2, which was the case before. Any other idea why this might be reasonable?
If there are like d plus 1 points, you can put them in each of the dimensions and like you can linearly separate each of them.
Why is that?
I was thinking that inhibits. I'm not sure.
I think you have the right idea that you can, there is a reason why you can, if you have few enough points, you can shatter them. That's what you're saying. Like in that example, you get 3 points, and if they were placed correctly, like one at the origin, one on the x-axis, the other on the vertical axis, then you can always shatter them. I think that's what you're saying, right? So that is true. Like if you have few enough points, then you have enough degrees of freedom in the model to realize all possible labels. So for example, the picture to keep in mind is in the case when d is 2, we were in 2 dimensions. We can maybe put 1 point at the origin, 1 point along the x-axis, the other point along the vertical axis, right? This seems like a good starting point. You just have to exhibit this, that was some set configuration of 3 points can be shattered. So how about this? Then I think you can easily argue that any labels you give, you can always find a way to separate them. So we'll try to formalize it, right? So the idea is this can be generalized. In d dimensions, you will have d axis and then the origin, and then you can have this cube, and then you can try to partition all the points. So, okay, so any other ideas?
So for any d, we're using d minus 1 to do the classification.
What does that mean? D minus 1?
So for d equals to 2, we'll use line to separate.
Uh-huh. So I guess what we are saying is there are d plus 1 parameters here. Look at the weight vector. How many free variables do you have? You have d plus 1 variables. And it is true to the first order that for most models, the VC dimension is good proxy to the number of free variables you have in the model. Here you have d plus 1 weight vector values, in your weight vectors. So you have d plus 1 free parameters to select in your model. And the VC dimension is exactly d plus 1. If you think of, say, a neural network with multiple layers, and you have a weight for each edge, and you count the total number of weights, that won't quite be the VC dimension, but the VC dimension will be close to it, and there are results that show it, right? So to the first order, the VC dimension is actually going to be close to the number of free variables in your model. And that's another way to sort of, that's the amount of freedom you have to fit the data. And the VC dimension is not, it's a formalization of that concept. It's not always the case. You can always construct contrived models where they can be very different. But for most practical models, they are the same to the first order. Any other thoughts?
In d-dimensional linear classification, your decision boundary is a d-dimensional hyperplane, and you need d points to define that hyperplane. Right? So if you have d plus 1 points, that's the maximum you can have, because d of those will be kind of defined by the hyperplane, and the other one will be the one that's separated.
Okay. So you're saying here there are 2 points define a line. But how does that help you to say that 3 points can be shattered? Because you don't, if the points lie on the decision boundary, they are considered misclassified.
Yeah, so if the line is like just next to the line that's defined by those 2 points, then that's how you separate this.
I see. You can essentially have the line very close to them if they are in the same label, if they have the same label. I might be able to argue from there. So I will give you a proof. The proof is a little abstract, but I think we have enough intuition now to appreciate how it is done. So we'll prove this. And to prove this, you have to do 2 parts. First, you have to show that if the number of points is less than or equal to d plus 1, then those points can be shattered. Meaning, give me any sequence of labels, I will find a weight vector that achieves it. And d plus 2 or more points cannot be shattered. So d plus 2 is a breakpoint. So to prove, we'll do it in 2 parts. So we'll consider the largest value of n. So let n be d plus 1. Then there exist n points. We'll show that there exists n points, say x1, x2 up to xn, that are shattered. So I just have to construct n points that are shattered. This is the first part. If n points are shattered, any subset of them is also shattered. That's clear, right? Because if you look at any subset of coordinates, all the combinations have to be there. And part 2 says that n equals d plus 2 is a breakpoint. And hence, any value of n greater than d plus 2 will also be a breakpoint. So,
Should n be d, not d plus 1?
So the VC dimension is d plus 1.
VC is d plus 1, right?
So up to d plus 1 points can be shattered, but d plus 2 or more points cannot be. So for part 1, we will say the following. Let y1, y2 up to yn, which are all -1 or +1. This is binary classification. So all the labels are -1 or +1. Be labels associated with x1, x2 up to xn. Okay? We want to show that there exists a W a weight vector such that y1 is the sign of W transpose x1, y2 is the sign of W transpose x2, and yn is the sign of W transpose xn. So we will specify what x1 to xn are. We are free to choose them. But let's say we have chosen them properly. Okay? Then we want to show that for any choice of y1 to yn, these are free labels. There are 2 to the n possible combinations of y1 to yn. For any combination you give me, I can exhibit a W such that you're correct on the first data point, you're correct on the second data point, and so on. Right? So going back to the case of 2 dimensions and n equals 3, no matter what y1, y2, and y3 are, I should be able to draw a line that is consistent with those labels. That is what we need to exhibit. So any ideas how you will do it? How will you end up approaching to find W from this? So any thoughts? So again, let's say x1 to xn are fixed. We have fixed them as some data vectors. So let's say that in this example, we have these 3 points, if you like. Okay, but let's say x1 to xn are some fixed vectors. I want to say that no matter what y1 to yn are, there will always be some W that I can compute such that these relations hold. So this looks a little complicated because sine is a nonlinear function. Okay, so let's do one simplification. Let's not worry about the sine. So let's say hypothetically I did not have a sine function. I just had y1 equals W transpose x1. I had y2 equals W transpose x2. So I do not worry about the sine function at all. Can I solve for W now? How?
Your y1 is g, right? G.
y1 is plus or minus 1.
Yeah, but it's if we like think about the
You combine them?
yeah, if you
Okay.
combine them,
So
it's
n
then
is b plus 1.
Yes.
Yeah.
And then the W transpose, you can think of it as a matrix as well, and your X as well, right?
Okay.
And then you just find
Okay, so the suggestion is that this is now a linear system of equations. Okay, how many unknowns do you have in this system? What are your variables?
W.
The W's, there are d plus 1 of them. How many constraints do you have? How many equations do you have? You have n equations, right? And it so happens in this problem n is in fact equal to d plus 1. So the number of equations equals the number of variables. So when will this have a solution?
When it's invertible, right?
When the system of equations is linearly independent. So all you require is that x1, x2 to xn be linearly independent, right? Because you can write this as was suggested. Let me do it on the next page once people are done copying. Okay. So before we go there, we went ahead and we removed the sine function. I said let's not worry about the sine function. What happens if I put it back in? What would change? Is it?
We constrained again, right? We now constrained by the sign.
So let's say I go back, I solve it by removing the sine function and then I put it back in. Will I still satisfy this or will I have a problem? So let's look at the first one. I have W transpose x1 and I've selected W, so this equals y1. So y1 is either plus 1 or minus 1. If say y1 is plus 1, what's the sign of plus 1? Plus 1. What if y1 is minus 1? What is the sign of this? minus 1. So it still works. The sign is doing nothing. It's just giving us more flexibility. But if you remove it, you can still solve it and the solution will be the exact solution. Right? The sign just thresholds things. So anything here positive would be labeled as +1, anything negative would be labeled as -1. You are being more strict now. You are forcing this argument to have a specific value. It has to be +1 or it has to be -1. Right?
About the case where it's 0.
We will never be, right? Because you are forcing this to be +1.
Okay.
By removing this sign, you are setting W transpose X1 to exactly equal Y1. So after you solve this system, this is exactly equal Y1. And sign of Y1 will be Y1. The sign function is really not changing anything if you solve this system. Okay, so what we can do now is you have y1, y2 up to yn. You can write it as x1 transpose, x2 transpose up to xn transpose times w. Now, if this matrix is invertible, so this is our data matrix, if you recall linear regression. X is in R n by d plus 1, and here n equals d plus 1. The question is, can you find x1 to xn so that this matrix is invertible? Or is it impossible to do that? So can you select x1, can you select x2 up to xn so that this matrix here is invertible? So remember, x1 is the first vector, so it will for all of them, the first coordinate has to be the bias term. So you cannot change it because we are in the augmented dimensions. Now you have to add some coordinates here. You are allowed to add d coordinates here. So all these vectors, the d plus 1 vectors are independent. Can you do that? So here is one example. You make this all 0. You make this 1, 0. And x3 will be 1, 0, 1, 0. So you just put like the remaining points on the axis as was suggested and one point at the origin. And this one.
There can be any real numbers.
They can be, there are many choices possible as long as they are independent. Because the only issue is you have one here, right? So that makes it, that puts a little bit of a constraint. They cannot be, this cannot be arbitrary. But the point is that this one you can verify, these vectors are linearly independent. No, none of them can be written as a linear combination of the others. So this solution, so you can use this as your data points. This matrix is guaranteed to be invertible. For any sequence of labels, you then just take W to be X inverse Y. That gives you a weight vector. And so what that gives you is that W transpose Xi will in fact equal Yi for I equals 1, 2 up to n. So sign of W transpose Xi will be the sign of Yi, but Yi is either +1 or -1 in binary classification. So this is actually equal to Yi. And you are done. Okay? So this proof formalizes the intuition we just discussed before we wrote this down. Why d plus 1 is a reasonable number. The number of variables here, the number of degrees of freedom you have is equal to the number of elements in W, which is d plus 1. So we can solve that many equations. So there was a second part. This is just one part. This shows that d plus 1 or fewer points can be shattered. But then there is a second part which says that d plus 2 or more points cannot be shattered. Now we could do this argument and we could say that if you put one more constraint, then you will have more equations than the number of variables. And then you will not be able to satisfy. Will that proof work, or is there a problem with that proof? So I could just extend this and I could say that, look, if you put one more row here, then you suddenly have more equations. You have d plus 2 equations, but d plus 1 variables. And that system cannot have a solution. So what's the problem with that proof? Any ideas? Why will that not work? Why can't I just extend this now and say that, look, if you set n to be d plus 2, then you have more equations than variables. And since we can select y1 to yn in an arbitrary manner, these are the labels, you cannot have, like this will in general not have a solution. You are just inverting, this matrix will now have this system will have fewer variables than the constraints. And y1 to yn can be any set of labels. So you will not be able to solve this. So what's the problem with that argument? If they can be dependent for one value of y1, but if I flip the other value, they will become, that part will be infeasible. You have to be able to do this for every 2 to the n choices here, right? So let's say for one choice you are lucky and they are consistent, so you can remove it. But then for the flipped value of y, it won't be consistent, and so it will fail. So that is clear. So it won't be able to solve this system if you have more equations than unknowns. But what fails?
Like the new value you added won't be independent anymore.
The
new value, like new accent you added won't be independent anymore.
No, so you are allowed to freely choose the x. So you can potentially select an x that works, right? But the problem is it has to work for all combination of the labels. So let's say you selected an x that is carefully chosen so that the system is consistent and you can eliminate one equation and you can go back to d plus 1 equations. But when you flip the value of the label, then it will no longer be consistent. And now you are in a case where you have more equations than unknowns and you won't be able to solve it. Right? So let's say I add one. Our decision rule was, where did it go? Back here, right? yi equals sine of w transpose xi. So if I show that here in this argument we're removing the sine function, right? We're just saying yi should equal forcing w transpose xi. So sure, if you remove the sine function and you say that now there is no solution, it does not necessarily refute the fact that if you put in the sine function, there is still no solution. Because this gives you a lot of freedom. Anything positive is allowed, anything negative is allowed. Here we were considering a very restricted case when we are forcing this argument to be exactly yi. So now you have to refute along with the presence of the sine function, okay? And so we cannot just do the equation counting argument. We cannot reduce it to linear systems. Is this clear? We want to show that n equals d plus 2 is a breakpoint. So we want to show that consider any, so you are allowed to select them in any way, any n equals d plus 2 points, x0, x1, x2 up to xd plus 1. And these are elements in Rd plus 1. Right? We want to show that they cannot be shattered by H. No matter how you select them, there will be some sequence of labels that we cannot achieve with a linear classifier.